Okay, so we're still working on population ecology. And in this screencast, we're going to be looking at how we estimate population size. So hopefully it would be so nice if we could get outside together, but we'll have to give that a try in the fall. And we've done some of it on our own anyway. But we're going to look at population size and how we measure it. And then we're going to evaluate and talk about how we can estimate sizes of fish in the ocean or lakes or rivers. And then finally, we will talk about how we can model population growth using something like duckweed. Okay, so first, let's take a look at some techniques to estimate population size. Okay, we've already done quadrat sampling, right? So you can go out and you can take your quadrat and put it out on the field and measure, how many plants are in that area and extrapolate the estimate for the whole entire field. But there's also something called the Lincoln Index, and this is for motile population. So if you want to measure how many mice there are in a field, you're not going to chase it around with a quadrat, right? You need to find a way to actually get a measurement where it's not going to be scared of you and run off. And you can do that by capturing them using cool traps. And so you can use these live traps to capture them and mark them. All right, so let's take a look at quadrat sampling one more time just for a review. Remember, we go out and we put our quadrats out to look at that. We can look at frequency, percentage cover, all those things. And you could do it in a transect, but we were doing it like in a field, right? So if you wanted to find in a grassy field how many dandelions there were, you put out a bunch of quadrats so you can see how you would count how many individuals were in each of those and then extrapolate the end. And you have to do it with a random number table, right? So you're not like purposefully going to places that have more or less or easier to get to. And then you count the density in those. And then you can extrapolate for the larger field to be able to get that. So you're just doing some sampling. But remember, you can't do that with with organisms that move around. And so you can use something called capture, mark, release, recapture. In the real wildlife world, they actually call it mark recapture, but IB refers to it as this capture, mark, release, recapture. And the way you do this is you go out and you capture a bunch of organisms in some way, shape, or form, and then you have to mark them. And then you release them and let them go back into their environment where they can reintegrate and do their normal daily lives. Then you put traps out again and you capture another sample from the population. And with that information, you're going to find out, okay, you know how many caught in the first capture, you know how many totally caught in the second capture, but then you also want to look at how many individuals in that second capture are recaptures that have that mark on it that you put on there. So you can see you put a little mark on those original ones. That mark's really important too, because you have to make sure the mark is not going to make them more susceptible to predation or hurt them in any way. Okay, so the numbers that you need to find, first you've got to calculate how many are in the first capture, or count how many are in the second capture, and then also how many of them were recaptured. Then you put them into this equation. So this equation is essentially the number of animals in the first sample, so this would be 1, 2, 3, 4, times the total number of animals in the second capture, 1, 2, 3, 4, 5. So 4 times 5, right? That's 20, divided by the number of animals in the second capture. And this one, so this is the number of marks. So our recaptured animals, there's 2. So that would be divided by 2. So 4 times 5 divided by 2. So we should get 10. So you're going to need to know this equation. So you want to take some time. You might see it as like M1 times M2. So divided by the number of marked captures, or N1 times N2 divided by M. So it'll be kind of different ways that they will represent those letters. But essentially, the total in the first capture times the total in the second capture divided by the remarked individuals in that second capture. Okay? All right. So now, how do we figure out the population of fish, say, in the Mediterranean or in the ocean? And because it's important to know that, because we want to know what is the sustainable yield of a fish population, because we want to know how many can we fish without collapsing the population. We want to be able to do it sustainably. And so sustainable yield is the number or weight of fish that can be removed by fishing without reducing the biomass of stock for the next year. So it's how to do it sustainably. How many fish can we take out and still have a rebounding population that'll be just as big as the original one? And if you are fishing at maximum sustainable yield, that's the absolute maximum that can be fished, right? But the problem is that we can't determine the sustainable yield or the maximum sustainable yield without being able to count the population or estimate the population. And we have to be pretty darn precise if we want to be able to not crash the population over time. So because data is never precise, it's better to fish well below what is the maximum sustainable yield, because if you didn't count correctly and you overfish, then you can actually crash the population out, and then you've lost your resource, could be permanently. You don't need to know these models, but you should be familiar with what this means. Now, do you recognize this? This is our logistic growth curve. And if we could estimate the maximum sustainable yield of fish, it would be exactly in the middle. It's half of carrying capacity. So right here you can see it's the carrying capacity divided by 2. So it's when it's growing at its absolute most exponential growth. Because what you can do is if there's, say, 500 fish is the carrying capacity, if you fish it down to 250 exactly, it should be that they can rebound in one reproductive cycle back to their carrying capacity. So you're essentially fishing them down where the resources are still abundant, so they just go boom, they replace their population back to carrying capacity, right? And so if you're fishing at carrying capacity at the maximum sustainable yield, right, then it's going to be actually not a ton of effort to be able to get like lots and lots of fish, right? So very, very, you can fish well and get lots of fish and be fine. But if you start to fish over that, so you bring that population down, then it actually makes it harder to find fish, and then you can actually deplete the population permanently. Just some, a little bit of math is just essentially, remember what determines a population. It's essentially birth and death. So birth minus death, and then immigration minus emigration. That's basically what this is right here. So it's how much bigger are the fish getting, and how many new fish are coming, how many fish are dying, and how many fish are, swimming away. So that's kind of how you start to think about what is that sustainable yield, because you want to be able to get it right in that perfect. Actually, you want to fish below it so you can still have plenty of fish to eat and you don't screw that up with your estimates. So how do they make those estimates? Well, I'm going to show you about making methods and estimating things, because it's actually really hard to do. You can't do mark recapture because the ocean is just way too big. So we tend to use fish catches. And so we actually have to do fish catches. But the thing is that when it's fish catches from like fisherman nets, the fish are already dead. So there's kind of it's not the greatest way to do it. And you also need fishermen to be able to cooperate and give you actual like real data, because if they weren't giving you the right data, then then you're not going to make an appropriate estimate. And the important thing for IB is that you can evaluate the methods used to estimate their stocks. That's kind of the key thing to what I'm talking about here. So you need them to be able to give you the right amount of like all their data that you get, so you can make a better estimate, right? But if they violate, like maybe they took a few more fish than they should have, and they don't want you to know it, then you can't make an appropriate estimation. If you want really good accuracy, you need to get data from a whole lot of fishermen. You need to cross-check their sales receipts with their logbooks, because they might be selling more than they're reporting. There should be observers on fishing vessels and processing plants and fish markets. You can soundtrack equipment to determine numbers, like sonar can kind of help give some ideas too. There's things like coded wire tags, so you can track fish a little easier. And they can also actually estimate the age of fish by coring their ear bones, so you can kind of know what is the age structure of the population, because a younger population has more potential to get bigger than if it's all just a lot of older fish. But I just want to show you with sustainable fishing attempts, like if you want to keep your population from crashing, and this isn't really something that's fully covered by the IB, but it is important when you're looking at fishing, is that you want to make sure you restrict catch on younger fish, like, and you can do that by having different size mesh. Make quotas, you can only catch so much. Let the fish breed without being disturbed. Have exclusion zones. Those are really nice, like marine protected areas. And drift nets, which are so terrible, and bottom trawlers. So let me show you what this style of fishing. So this is a bottom trawler, and essentially it's clear cutting the bottom of the ocean. How awful is that? And it's just going to rip away everything so you can see what's left over. And also, if you put out drift nets that get, there's a lot of ghost nets and other things that get away. Well, you're catching things that you don't necessarily want to catch. And so all of these things, you can't really keep things that you don't want to catch out of those nets. And so it's pretty terrible. So you don't want to be using these drift nets and the bottom trawlers, because you can catch a lot of different things and you can really destroy the habitats. Okay. The last thing that you need to know for this unit is, what would you do to estimate the population of something like Lemna minor, which is duckweed? And you can actually do this for your IA in the fall if you're interested. It's pretty cool. So you can grow this cool duckweed this is duckweed. We can collect it out of the ponds in the forest nearby. And if you put some into little, cups, you can watch it grow. It clones itself. It actually has these cool little roots, and you can count how many there are. So if you put like 5 of them into a cup, after like a week, you might have 10. So they grow pretty quickly and they clone themselves. And so you can count how many there are. And if you grow them in a cup, you can actually mark their population growth over time. And eventually in that cup, they might reach carrying capacity, right? And you can also track what their population growth is, and like what is their biotic potential, like how fast are they growing. And there's a cool equation. You don't need to know this equation right now, but just if you did decide to do this, I can show you how to use this equation to be able to determine the intrinsic rate of growth and how fast they're going when they're at their biotic potential. So you can kind of see, oh yeah, how quickly do they grow, and what's the carrying capacity. And if you were to manipulate a variable, you could, change the size of the container. You could add more or less nutrients, the amount of light, the color of light. There's a lot of different ways that you can manipulate different variables. So you could have some cups that are, under dimmer light, and some are under brighter light. It could be the number of light hours. You could use UV. So there's a lot of different things you can manipulate. It's a pretty good lab. Okay. So you do, though, even if you don't do the lab, you need to be able to talk about how you could use a sample organism to determine the growth rate, just, how quickly you can model it, how quickly it's growing, and then the carrying capacity. Okay.